Hello, mic testing 1, 2, 3. Hello. Hello. Mic testing 1, 2, 3. Hello.
Oscillations, spring, pendulum. Oscillations due to a spring, so that it executes to and fro motion or is equal to mass of the block plus A minus A is equal to maximum displacement. X is equal to 0 equal to position of the center of the block at the equilibrium of the spring. When the spring is deformed, it is subjected to a restoring force Fx, which is proportional to the displacement x in the opposite direction. Fx is proportionate to minus x. Therefore, Fx is equal to minus kx. Equation 1. K is the spring constant, which depends on the property of the spring. Using Newton's second law of motion, the force applied to pull the spring, F is equal to ma, which must be equal and opposite to the restoring force. Since acceleration in SHM is equal to minus omega square x, therefore F is equal to minus m omega square x. On comparing it with equation 1, Fx is equal to minus kx, we get k is equal to m omega square. Omega is equal to root k upon m, where omega is the angular speed of the spring. Time period t of the oscillator is t is equal to 2 pi upon omega, or t is equal to 2 pi root m upon k. Damped simple harmonic motion. In this module, we will learn about damped simple harmonic motion. Damped simple harmonic motion can be simply explained with a mass connected with spring and a block system. A vane is connected with the block, which remains submerged in water as shown. You will notice that as the block oscillates up and down, the displacement on graph reduces with time. Thus, a simple harmonic system that oscillates with decreasing amplitude with time is called damped simple harmonic oscillation. Some very important points regarding damped simple harmonic motion are that in damped simple harmonic motion, the energy of the system is dissipated. That is, the damped simple harmonic system constantly loses energy. Damping force Fd, which damps the oscillatory motion, depends on the nature of the surrounding medium. It is proportional to the velocity v of the block and acts opposite to the direction of velocity of the block. That is, Fd proportional to minus v. Fd is equal to minus bv, where b is equal to positive constant, depends on characteristics of the medium such as viscosity, the shape, and size of the block. It is very important to understand that when a mass m attached to a spring is released, it settles to a height. When the mass is pulled up or down, the restoring force Fs on the spring is proportional to the displacement x from its equilibrium position. By equation, Fs proportional to minus x, or Fs is equal to minus kx, where x is the displacement from the equilibrium position and k is the spring constant. Let us combine both the equations. Now, according to Newton's second law of motion, net force acting on the body is equal to damping force plus restoring force, which is equal to ma into t is equal to minus kx into t minus bv into t from the previous equations, which in turn becomes m d square x upon dt square plus b dx upon dt plus kx is equal to 0. On finding the solution to the equation, we get x into t is equal to a into e raised to the power minus bt upon 2m cos omega prime t plus phi. Here, a into e raised to the power minus bt upon 2m is the amplitude. Omega prime is equal to angular frequency of the damped oscillator. Omega prime is equal to whole under root k upon m minus b square 4m square. It is very important to note that x into t is equal to a into e raised to the power minus bt upon 2m. Cos into omega prime t plus phi is not periodic because e raised to the power minus bt upon 2m decreases continuously with time. Hence, the amplitude keeps on decreasing with time. The mechanical energy in the damped system is represented as E is equal to 1 upon 2 Ka square, E raised to the power minus Bt upon m. The equation shows that the total energy of the system decreases exponentially with time. It is important to note that for small damping, B upon under root 2 Km, much less than 1. Oscillations and Resonance, Part 1. Let us now understand about forced oscillations and resonance. Forced oscillations and resonance can be explained by a spring attached with a ball and a hand on the other side. Now, if the ball goes up and down, the oscillations die out with time due to damping. However, if the hand also goes up and down along with the ball, this external force of the hand gets applied to the system, and now the ball starts oscillating without dying out. An associated term with forced oscillations and resonance is called as natural frequency. Let us learn about the terms related to forced oscillations and resonance. If no external force acts on a system, the system will execute oscillations of frequency nu naught. That is called as natural frequency. The oscillations produced under the effect of an external periodic force of frequency other than the natural frequency of the oscillator are called forced oscillations. If an external force Ft is applied to a damped oscillator, then Ft is equal to F naught cos omega dt. Let us label this as equation 1, where F naught is equal to amplitude of external force, omega d is equal to driven frequency. The motion of a particle under the combined action of a linear restoring force, damping force, and a time-dependent driving force, as represented by equation 1, is given by MAD is equal to minus KXT minus BVT plus F naught cos omega dt. M d square x upon dt square plus b dx upon dt plus kx is equal to F naught cos omega dt. Let us label this as equation 2. The displacement after the natural oscillation dies out is given by xt is equal to a cos omega dt plus phi. Amplitude A is the function of the forced frequency omega d, and the natural frequency omega. Forced oscillations and resonance, part 2. Analysis shows that amplitude is given by A is equal to F naught upon square root m square omega square minus omega d square whole square plus omega d square b square. Let us label this as equation 3. Tan phi is equal to minus v naught upon omega dx naught, where m is equal to mass of the particle, v naught is equal to velocity of the particle at t is equal to 0, x naught is equal to displacement of the particle at t is equal to 0. Omega is equal to natural frequency. Let us take some cases. Case 1. Small damping, driving frequency far from natural frequency. In this case, omega dB will be much lesser than m omega square minus omega d square. Omega dB less than m omega square minus omega d square. Therefore, A is equal to F naught upon m into omega square minus omega d square from equation 3. Case 2. Driving frequency close to natural frequency, or omega d is very close to omega. M omega square minus omega d square would be much lesser than omega dB for any reasonable value of b. M omega square minus omega d square less than omega dB, then the equation 3 reduces to A is equal to F naught upon omega dB. The amplitude is greatest near omega d upon omega is equal to 1. The 5 curves correspond to different extents of damping present in the system. Curve A corresponds to the least damping, and damping goes on increasing successively in curves B, C, D, and E. Notice that the peak shifts to the left with increasing B. The phenomenon of increase in amplitude when the driving frequency is close to the natural frequency of the oscillator is called resonance. Resonance. Now let us learn more about the phenomenon of resonance. In the previous module, we have learnt about the phenomenon of forced oscillations and resonance. The phenomenon of increase in amplitude when the driving frequency omega d is close to the natural frequency omega of the oscillator is called resonance. The amplitude is greatest near omega d upon omega is equal to 1. Here we have a set of 5 simple pendulums of assorted lengths suspended from a common rope as shown. Every pendulum has a natural or resonant frequency, which is the number of times the pendulum swings back and forth per second. Time period of simple pendulum is directly proportional to the square root of its length. T is proportional to root L, and nu is equal to 1 upon T. Longer pendulums will have lower frequencies. Since frequency is inversely proportional to time. Here you can observe that the pendulums 1 and 4 have the same lengths and the others have different lengths. Now let us set pendulum 1 into motion. The energy from this pendulum gets transferred to the other pendulums through the connecting rope and they start oscillating. The driving force is provided through the connecting rope. The frequency of this force is the frequency with which one pendulum oscillates. We observe that pendulums 2, 3, and 5 first start oscillating with their natural frequencies of oscillations and different amplitudes. But this motion is gradually damped and not sustained. Their frequencies of oscillation gradually change and ultimately they oscillate with the frequency of pendulum 1. That is, the frequency of the driving force but with different amplitudes. They oscillate with small amplitudes. The pendulum 4 oscillates with the same frequency as that of pendulum 1. And its amplitude gradually picks up and becomes very large. A resonance-like response is seen. This happens because in this the condition for resonance is satisfied. That is, the natural frequency of the system coincides with that of the driving force.
Let's do this question. A particle executes simple harmonic motion given by y is equal to 0.24 sine 400t plus 0.5 in SI units. What we have to find is amplitude, frequency, and time period of vibration. Let's do this. So here y is equal to 0.24 sine 400 t plus 0.5, and what we can do this is we can compare this with standard equation of simple harmonic motion, which is a sine omega t. So then we will have, when we compare these, we will have first amplitude. First we can find amplitude. Amplitude A is equal to 0.24 meters since we are doing in SI units. Second, we have to find the frequency, and if we compare the two equations, then we can see that omega is equal to 400. This implies 2 pi frequency is equal to 400. This implies we can find frequency as 400 by 2 pi. So when we calculate this, this will come as 63.6 hertz. Third, we have to find the time period. So t will be equal to 1 by frequency is equal to 1 by 63.6 seconds is equal to 0.0157 seconds. Let's do this question. Equation of simple harmonic motion are given by y is equal to 3 sine 5 phi t plus 4 cos 5 pi t, where y is in centimeter and t is in seconds. Determine the amplitude, period, and initial phase. So here in this question, the given equation is y is equal to 3 sine 5 pi t plus 4 cos 5 pi t. And for solving this, let a cos phi is equal to 3 and a sine phi is equal to 4. Then on squaring and adding, we have a square cos square phi plus a square sine square phi is equal to 3 square plus 4 square. So this implies taking a square out. Inside the bracket we will have cos square phi plus sine square phi is equal to, this will be 3 square is 9 plus 4 square is 16. This implies a square is equal to 25. This implies taking square root on both sides, a is equal to 5. Or rather we can write a is equal to 5 centimeters. Also we will have, if we divide these, we can write a sine phi over a cos phi is equal to 4 by 3. This implies a cancels with a and sine phi by cos phi is tan phi. So tan phi is equal to 4 by 3. So 4 by 3 is 1.3333. This implies phi is equal to tan inverse of 1.333. So this implies phi is equal to 53 degrees and 8 minutes. So what we can do is, if this is equation 1, so we can rewrite equation 1 as y is equal to, in place of 3, we can write a cos phi sine 5 pi t plus for 4 we can write a sine phi cos 5 pi t. This implies y is equal to, taking a common, this becomes the formula of sine a cos b plus sine b cos a. So that becomes a sine 5 pi t plus phi. So this implies y is equal to In place of A here we can write 5 sine 5 pi t, plus in place of 5 we can write 53 degrees and 8 minutes. And we can call this as equation second. Now what we will do is we will compare equation second with y is equal to a sine omega t plus phi. On comparison, we can see that A, the amplitude is 5. So I can write here, therefore, amplitude is equal to 5 centimeters and omega is equal to, so here if we compare this, omega is equal to 5 pi. This implies omega is given by 2 pi by capital T. So that is equal to 5 pi. Pi and pi get cancelled. So this implies from here T is equal to 2 by 5 is equal to 0.4 seconds. And also by comparing the two, we can get initial phase phi is equal to, initial phase phi is equal to 53 degrees and 8 minutes. A man stands on a weighing machine placed on a horizontal platform. The machine reads 50 kg. By means of a suitable mechanism, the platform is made to execute harmonic vibrations up and down with a frequency of 2 vibrations per second. What will be the effect on the reading of the weighing machine? The amplitude of vibration of platform is 5 centimeters and take here G is equal to 10 meters per second. So here in this question, mass is equal to 50 kg and frequency here is 2 second minus 1 and amplitude is given as 5 centimeters, that is equal to 0.05 meters. And we know that maximum acceleration A max is equal to omega square A. So that is equal to omega we know is 2 pi nu whole square multiplied by AA here is 0.05 is equal to 4 pi square nu square multiplied with 0.05. So this is equal to 4 multiplied by 22 by 7 whole square multiplied by square of the frequency. Frequency is 2, so that becomes 2 square is 4 multiplied with 0.05. Of course, meters per second square, the units. So when this is calculated, this comes as 7.9 meters per second square. Therefore, max, that means maximum force on man is equal to, force is always mass into acceleration. So that will be G plus A max. So that is equal to 50 multiplied with G is 10 plus 7.9 newtons. This is 50 multiplied with 17.9 newtons. This is equal to 895 newtons, and converting this into kg force will be 89.5 kilogram force. Also, we can also find the minimum force on man. Minimum force on the man will be M multiplied by G minus A max. So that will be equal to, in place of M, we'll write 50. 10.0 minus 7.9 newtons. This is equal to, when calculated, this comes as 105 newtons. So that is 10.5 kilogram force. So here we have calculated the maximum force on the man and the minimum force on the man. Therefore, we can say that, therefore, reading on the machine, that means the weighing machine. So reading on the machine varies between 89.5 kilogram force and 10.5 kilogram force. Let's do this question. A mass of 1 kg is executing simple harmonic motion, which is given by x is equal to 6.0 cos t plus pi by 4. What we have to find here is, what is the maximum kinetic energy? So in this question, mass is equal to 1 kg, and the given equation is, x is equal to 6.0 cos 100t plus pi by 4, and comparing this with standard equation, that is, x is equal to a cos omega t plus phi. We will have, this implies a is equal to 6.0, omega is equal to 100, and phi is equal to pi by 4. And what we have to find here is maximum kinetic energy. That will be equal to half mv max square. So that is equal to 1 by 2. Mass is 1 and v max square is a omega whole square. This is equal to 1 by 2 multiplied with 1. And A here is, we've calculated A as 6.0 and this is in centimeters. So this will be converting this into meters. This will be 6 by 100 multiplied with omega. Omega is 100 whole square. So this becomes 18 joules. Let's do this question. An 8 kg body performs simple harmonic motion of amplitude 30 centimeters. The restoring force is 60 newtons when the displacement is 30 centimeters. What we have to find here is the time period, the acceleration, potential energy and kinetic energy when the displacement is 12 centimeters. So let's see what is given here. Here mass is given as 8 kg. And amplitude is given as 30 centimeters, and we can always convert this into meters. So that is 0.30 meters. Let's do the first part. That's the A part. Here it is given that force is equal to 60 newtons when displacement, let's say y, is equal to 30 centimeters, that is 0.30 meters. And we know that force is equal to Ky, or K is equal to F by Y is equal to 60 by 0.30 equal to 200 Newton per meter. So omega we know is given by square root of K by M is equal to square root K. For K we can write 200 by M. M is 8. So that is equal to 5 radians per second. Also, omega is equal to 2 pi by capital T. So this implies T is equal to 2 pi by omega. So that is equal to 2 multiplied by 22 by 7 multiplied with omega is 5. So when this is calculated, time comes as 1.256 seconds. Let's do the B part. In B part, it is given that displacement y is equal to 12 centimeters. So that is equal to 0.12 meters. Therefore, acceleration is equal to omega square y. So this implies capital A is equal to omega square, that means 5 square multiplied with 0.12 meter per second square. This implies A is equal to 3.0 meter per second square. We know that potential energy is given by half Ky square. So that is equal to 1 by 2. For K we can write K we have calculated as 200 multiplied with y square is 0.12 whole square. This will be equal to 1.44 joules, and kinetic energy is given by the formula 1 by 2 K. Inside the bracket we have a square minus y square. This implies kinetic energy is equal to 1 by 2. For K we will write 200. A square minus y square will be, amplitude here is 30 centimeters, so this is 0.30 square minus y square will be 0.12 square. And when this is calculated, this comes as 7.56 joules. Let's do this. A period of oscillation of mass m kg is suspended by an ideal spring of 1.5 seconds. If additional mass 3 kg is suspended, the time period is increased by 1 second. Find the value of m. Let's solve this. In first case, T1 is equal to 1.5 seconds, and let mass is equal to m kgs, and as time period is given by 2 pi square root m by k. So this implies time period is equal to 1.5 is equal to 2 multiplied by 22 by 7 m by k inside the square root. And let's take the second case. In second case, T2 is equal to 1.5 plus 1 is equal to 2.5 seconds, and mass is equal to m plus 3 kgs. Then here, using the same formula, we will have, so here we will have 2.5 is equal to 2 multiplied by pi is 22 by 7 square root m plus 3 by k. If we can call this as 1, then we can call this as second. And now what we will do is dividing 2 by 1. So this implies 2.5 by 1.5 is equal to square root of m plus 3 by m. This implies, squaring both sides, we will have 25 by 15 whole square is equal to m plus 3 by m. This implies we will have 5 square by 3 square is equal to m plus 3 by m. So this implies we will have 25 by 9 is equal to m plus 3 by m. This implies 25m is equal to 9m plus 27. This implies we will have from here we can have m is equal to 1.69 kgs. So this is what we have to find here. Let's do this question. Two identical springs, each of force constant K, are connected in series and parallel, turn by turn, and they support a mass capital M. We need to calculate the ratio of the frequency of oscillation of the mass in two systems. Let's solve this. First, we will consider series combination. So let me write it down. For series combination, Ks, that is the effective force constant, is given by K multiplied by K divided by K plus K. So that will be equal to K by 2. Therefore, we can say that frequency nu for series will be equal to 1 by 2 pi square root Ks by m is equal to 1 by 2 pi square root. For Ks, we can write K by 2 and m here. Now let's take part B. For parallel combination, effective force constant Kp is equal to K plus K is equal to 2K, and mu P will be equal to 1 by 2 pi Kp by m. This is equal to 1 by 2 pi. And for Kp here, we can write K plus K by m. So this is equal to 1 by 2 pi. In the bracket, we will have 2K by m. And what you can do here is you can call this as first and this as second. Therefore, ratio of frequencies, this is what we have to find in the question. Ratio of frequencies is equal to 1 by 2 pi square root K by 2 by m divided by this, that is 1 by 2 pi square root 2K by m, and this will come as 1 by 2. So this is the ratio of the frequencies in series combination and parallel combination. Let's do this question. Two identical springs. Let's do this question. A 5 kg collar is attached to a spring of string constant 500 Newton per meter. It slides without friction on a horizontal rod. The collar is displaced from its equilibrium position by 10 centimeters and released. Calculate the period of oscillations. So what we have to calculate here is the period of oscillations, the maximum speed and maximum acceleration of the collar. Here, mass small m is equal to 5 kg and the spring constant is given as 500 Newton per meter, and maximum displacement here, that means amplitude A, is given as 10.0 centimeters. So we can always convert this into meters. That will be 0.1 meters. So let's see what we have to find. The first thing, let's take part A. First, in part A, we have to find the time period. Time period is equal to 2 pi square root m by k is equal to 2 pi square root. For mass, we can write 5 kg divided by k here is 500. So that will be equal to 2 pi by 10 seconds. When calculated, this will come as 0.628 seconds. Moving over to part B, and in part B, we have to find the maximum speed. Maximum speed is given by the formula. Omega is equal to 2 pi by t. So that will be equal to 2 multiplied by pi and divided by time period. So that is 2 pi multiplied with 10. 2 pi cancels with 2 pi here, and this comes as 10 radians per second. And we know that